For over 40 years, Voyager 1 has been our loneliest ambassador, whispering back from the void. Then, a cosmic ray strike scrambled its mind. The signals went silent. We thought we had lost our link to the stars, but a brilliant act of cosmic surgery revived it across billions of miles. Voyager is speaking again. It's giving us our first look at a universe that is not empty, but vibrantly alive. Its groundbreaking data on plasma and radiation will help us prepare for the next steps into the great unknown. 15 billion miles from Earth, Voyager 1 is whispering back signals from a place no human-made object has ever sampled directly. In this video, we will explain the Sun's protective bubble, the heliosphere, and why crossing its edge, the heliopause, matters. We will trace Voyager 1's telemetry failure in late 2023 and its recovery by mid-2024, walk through what each instrument is hearing in plain terms, and show how NASA checks signals from a spacecraft that old to guide future missions. For months, those signals turned into static, and it seemed we had lost our link to interstellar space. But NASA engineers revived the spacecraft with a careful memory reprogramming across billions of miles. Now, its instruments are speaking again, and they hint at a persistent plasma hum, a shifted and turbulent magnetic field, and steeper cosmic ray levels. To see why these findings matter, we first need to understand the shield Voyager has now passed beyond, the Sun's shield and the mysterious edge. What makes the Sun's shield so important is that it is not empty space but a defined region called the heliosphere. This vast bubble forms where the solar wind, an ongoing flow of charged particles carrying the Sun's magnetic field, pushes outward against the galaxy. At its outer edge lies the heliopause, the boundary where the outward pressure of the solar wind balances the interstellar medium, the thin mixture of plasma, dust, and radiation that fills the space between stars. Inside this shield, Earth and the other planets are partly protected from the full intensity of galactic cosmic rays. Without it, radiation levels on our planet's surface would be much higher. The heliosphere is often pictured as a bubble blown by the sun, but in reality, its shape is sculpted by both the solar wind and the pressures of the surrounding interstellar medium. It extends far beyond Pluto, billions of kilometers in every direction, before the Sun's influence weakens enough to yield to the galaxy. For years, scientists expected the transition out of this bubble to be gradual, fading smoothly into interstellar conditions. Voyager 1 revealed that idea was incomplete. The crossing is sharp, sudden, and more abrupt than many models predicted. On Earth, our atmosphere shields us from harmful radiation and the vacuum of space. The heliosphere serves a similar but larger scale role for the entire solar system. Outside of it, the background conditions change. The density of cosmic rays rises, plasma turbulence intensifies, and even the direction of the measured magnetic field shifts. The environment becomes harsher for spacecraft electronics and for any hypothetical crew who might one day venture beyond. It is not a complete loss of protection, since natural shielding from spacecraft design still matters, but it does represent a step into a setting where radiation levels and magnetic disturbances are significantly higher. Voyager 1 provided our first direct observations of this environment. In 2012, its instruments recorded a clear shift as it crossed the heliopause. Detectors that had measured charged particles carried by the solar wind suddenly reported their decline, while the cosmic ray sensor registered a sustained jump in high-energy particles coming from deep space. The consensus view is that this jump marks entry into the galactic environment rather than a temporary solar event. It established that Voyager had passed fully outside the Sun's domain and into a region shaped by countless past supernovae and other stellar processes. This transition matters for both science and engineering. For spacecraft design, the steady rain of cosmic rays outside the heliosphere can disrupt electronics, trigger errors in memory storage, or distort signals. For human missions, it sets a clear note of caution. Any long-duration travel beyond the Sun's shield would demand far more robust protection than we currently use near Earth, or even at Mars. The heliopause is not just a scientific term. It is a functional dividing line that dictates how fragile or resilient a system needs to be in order to survive. Voyager's instruments captured this boundary crossing with stark clarity. Particle counts tied to the solar wind decreased, galactic cosmic rays surged to a new baseline, and the magnetic field orientation shifted. These results confirmed that interstellar space is not silent or empty. It is active, filled with plasma fluctuations, magnetic currents, and high-energy particles accumulated over millions of years. Voyager showed us that this environment is real, measurable, and distinct from the Sun's protective bubble. The crossing also highlighted a deeper tension. While Voyager revealed a new space environment, the probe itself has grown increasingly fragile. Its instruments continue to operate, but its systems are aging, and recent problems have threatened to cut off that view entirely. So, if the heliopause altered Voyager's readings years ago, why has its recent outage and recovery changed what we can learn now? That's next. Voyager's near silence and unexpected revival. In late 2023, Voyager 1, the spacecraft that had carried our reach into interstellar space, seemed to fall quiet. Telemetry, the status and science data a spacecraft sends back, is the mission's lifeline. Without it, engineers cannot know whether a probe is warm or frozen, stable or failing. Instead of usable streams, Voyager 1 began transmitting signals that were scrambled. They still reached Earth, but the content no longer matched health reports or science measurements. To controllers at NASA's Jet Propulsion Laboratory, it felt as though the probe had slipped into a kind of nonsense after nearly 5 decades of clarity. The problem was deeper than one broken reading. It masked every measure of the spacecraft's condition. Remote troubleshooting is always demanding, but here the craft revealed almost nothing about what had gone wrong. Each command sent outward took nearly a day to travel the 15 billion miles, and another day for a reply. With every adjustment taking roughly 2 days for confirmation, the pace of recovery was agonizingly slow. By early 2024, analysis converged around a likely cause. Engineers suspected a fault in the flight data subsystem, the computer responsible for packaging measurements for transmission. Evidence pointed toward a corrupted memory bank. The working hypothesis was that a high-energy cosmic ray particle had struck a chip and disabled part of it permanently. In deep space, outside the Sun's protective bubble, such radiation strikes are not just possible, but expected. Unlike a computer on Earth, Voyager 1 could not swap parts or replace modules. An entire section of memory was, in effect, burned out. Restoring the subsystem was nothing like pressing a reset button. Engineers were faced with a delicate reprogramming task. A useful analogy is repairing a library catalog when part of the index has been destroyed. The books, or in this case, the instruments, still exist, but without a working index, they remain inaccessible. The team's solution was to move essential code and housekeeping routines out of the damaged memory and relocate them into surviving regions. Redistributing instructions in this way let the spacecraft bypass the corrupted block while still recognizing its commands. Executing this repair required extreme caution. Every line of code had to be rewritten with minimal disruption. With a 2-day round trip for every test, a mistake could leave the spacecraft unresponsive. Engineers effectively performed brain surgery over a single thread of communication, slowly patching the system back together piece by piece. On April 20th, 2024, the first clear breakthrough arrived. Health telemetry once again reached Earth in a form engineers could read. The trickle of data confirmed Voyager 1 was still alive. Over the following weeks, the mission team worked systematically to restore its science payload. By June 2024, engineers had brought the active instruments back online, including the plasma wave system, the magnetometer, and the cosmic ray detector. Gradually, the spacecraft resumed its role as a working outpost in interstellar space. The achievement was more than technical repair. It showed that hardware launched in 1977 could endure a cosmic ray strike nearly 50 years later and still respond to careful reprogramming. The episode underscored both the vulnerability of electronics outside the Sun's protective heliosphere and the resilience embedded in Voyager's design and operations. It demonstrated that even with aging parts and limited memory, patience and precision from Earth could restore a voice we had nearly lost. With the craft speaking again, we can now re-evaluate whether the new readings reflect real interstellar features or the effects of aging instruments, a challenge the science team must address next. Signals from the interstellar frontier. With its instruments restored, Voyager 1 was once again able to return information from the edge of the Sun's domain. The signals now arriving are shaped by 3 detectors that act like investigators: the plasma wave system, the magnetometer, and the cosmic ray detector. Each contributes a different strand of evidence about what interstellar space is actually like. The first of these is the plasma wave system. Plasma is a state of matter made up of charged particles, mostly electrons and protons, that fills much of space. Early expectations were that the plasma outside the heliosphere might be nearly uniform and quiet. Voyager's recordings revised that picture. The plasma wave system detects persistent low-frequency oscillations in the surrounding medium. The pitch of those oscillations is used to estimate local electron density. Instead of silence, the spacecraft registers a faint, continuous hum whose changes show that interstellar plasma varies in density over time. These variations tell us that the region beyond the heliopause is textured and active, not a simple void. The magnetometer provides the next view. A magnetometer measures the strength and direction of magnetic fields, which inside the heliosphere are dominated by the Sun and shift with solar activity. In interstellar space, the expectation had been for a weaker, smoother galactic magnetic field. Voyager's readings showed otherwise. The field outside is stronger than predicted and tilted at a noticeable angle compared with the solar field inside the bubble. This suggests that the boundary between the two regions is sharp rather than gradual, with distinct orientations on either side. In addition, Voyager continues to register fluctuations, turbulence that shows the galactic field is stirred rather than calm. The consensus interpretation is that this combination of tilt and turbulence comes from normal features of the galactic magnetic structure and the lingering effects of past supernova explosions that ripple through space. This explanation fits the data without requiring more unusual causes. The third instrument still returning crucial values is the cosmic ray detector. Cosmic rays are high-energy particles that move near the speed of light, most of them produced by stellar explosions or intense stellar activity. Earth's magnetic field and atmosphere provide partial protection against them, and inside the heliosphere, their intensity is also moderated. Once Voyager crossed the heliopause, however, its readings showed a clear rise in cosmic ray counts. That higher baseline has remained steady, representing a significant change compared to conditions under the Sun's shield. For spacecraft electronics and potential crew, this implies a higher steady background of high-energy particles beyond the heliopause. Designing for these conditions requires more robust shielding and electronics that can withstand frequent particle strikes. Taken together, these three perspectives show that models picturing interstellar space as smooth and empty were incomplete. The new data reveal density shifts, turbulent magnetism, and constant radiation pressure. A good analogy is an ocean surface seen from afar, which may look calm. When examined closely, currents, ripples, and wave patterns become clear. Voyager demonstrates that the interstellar medium is the same, structured, active, and imprinted with the history of ancient stellar events. An essential question naturally follows. Are the features reported by Voyager genuine measurements of interstellar space, or could they be artifacts created by an aging spacecraft nearly 50 years old? The mission team approaches this cautiously. They rely on cross-checks between instruments, patterns that repeat over time, and staged reactivation of subsystems to confirm whether signals are consistent with the surrounding environment or with possible onboard faults. How those checks separate reliable evidence from possible errors is the next step in understanding the story these signals tell. Sorting evidence from speculation. Sorting evidence from speculation becomes essential whenever spacecraft data reveal the unexpected. Voyager 1 sits at the center of this challenge because it samples a region no other probe has touched. Each strange flicker in its readings sparks questions, but not all questions carry the same weight. Some ideas are hypotheses, plausible but unproven explanations that require supporting evidence. Others drift further into speculation, and without data, they remain unsupported claims rather than testable science. The cautious mainstream interpretation stresses natural causes in the interstellar medium. Plasma, the sea of charged particles flowing between stars, is shaped by supernova remnants, expanding shock waves, and broad galactic magnetic fields. Astronomers sometimes call this galactic weather, since it varies much like patterns in Earth's atmosphere. When Voyager records sustained plasma oscillations or sudden magnetic shifts, the consensus is that it is measuring these natural processes. The complexity is new, but it does not demand extraordinary mechanisms to be credible. Speculative hypotheses gain attention because of the mystery. For example, some suggest that radiation patterns could form deliberate structures, perhaps designed as communication or navigation markers. That is a hypothesis with no supporting evidence in Voyager's data. The scientific consensus is that natural plasma physics and magnetic structure explain the observations more effectively. Other voices argue that turbulence could conceal organization not produced by known physics, but these too fall into the realm of speculation. In science, the principle is clear. Evidence must come first, and simpler explanations must be tested before unusual ones are embraced. The strength of the evidence-based view comes from verification. Mission teams follow conservative checks to confirm that new signals reflect the local environment, not aging instruments. They compare simultaneous measurements across instruments. A rise in plasma density, for instance, should align with related changes in the magnetic field if the cause is real. They examine repeatability through time series patterns, looking for correlations with known events, such as solar outbursts. They stage reactivation of subsystems to isolate potential faults, step by step, rather than assuming a reading reflects the environment. Finally, they cross-check basic spacecraft telemetry, the housekeeping data on temperature, power, and system health, to ensure no malfunction is interfering. These steps create a layered process that favors caution and builds a chain of confidence in the results. There is a case study from Voyager's past that illustrates this approach. Years ago, the spacecraft registered periodic bursts in plasma readings that puzzled researchers. To some outside observers, the unusual pattern hinted at non-natural activity, but deeper analysis linked those bursts directly to shockwaves from past solar storms, traveling outward and only arriving at Voyager after years of delay. What initially looked unfamiliar turned out to be solar behavior observed at an extreme distance. Mystery was translated into mapped physics by steady, careful interpretation. The broader point is that uncharted space naturally produces signals we cannot yet model fully. That uncertainty leaves room for hypotheses, but until new evidence arrives, the consensus remains with well-understood plasma physics and galactic magnetism. The interstellar medium itself is already extraordinary, dense with charged particles, turbulent magnetic fields, and constant cosmic rays. Science benefits most when interpretations highlight what is supported and mark other ideas as untested. Voyager demonstrates how patient cross-checks uphold credibility, even though its parts are decades old and isolated nearly 15 billion miles away. That discipline is why most scientists prefer natural explanations first, and why extraordinary claims need extraordinary evidence. And with that framework in mind, we can now step back and see the larger picture of what Voyager has already shown us beyond the Sun's shield. Conclusion. Voyager has confirmed that interstellar space is not quiet, but active and measurable. Its instruments show plasma that hums with density changes, magnetic fields that tilt and fluctuate, and cosmic rays that rise beyond the Sun's shield. These are direct observations, not just models. Its 2024 recovery also proved that hardware launched in the 1970s could be reprogrammed across billions of miles, bringing critical instruments back online. The practical implications are clear. Voyager's maps of higher particle fluxes guide route planning. Its fragile computers highlight the need for radiation-hardened design, and its long record gives a rare baseline for galactic weather. Share what you'd like explained next in the comments, or subscribe if you want calm, source-based updates on Voyager and upcoming missions. We'll continue to report what the data show, and we'll flag when a claim moves from hypothesis to supported conclusion.